Hi, welcome to Munro Live. I'm Paul Turnbull. I'm with Munro Associates. We're an engineering consulting company, and we do tear down some parts. And there's been a lot of interest recently in axial flux motors, electric motors. And so we took one apart. Sandy decided to buy this one from Powertrains. It's a Shanghai company that makes these axial flux motors. It's a really great example of axial flux motors, and this particular one came with two motors stacked together attached to transmission. And we took one of those motors and tore it apart, so you can see, first of all, here's what one looks like before you take it apart, and then we removed this plate here and then the gasket, so you can see the cooling channels for how this motor is cooled. And real quick, I just want to talk about how this is really cooled. Here we have what's a water cooling system. And the nice thing is that this keeps the water separate from the windings. If there is a leak, it leaks outside the motor, not into the windings. So you have cool water coming in here, and then it goes through the serpentine path and then circling around back out here. And by doing this, you have cool water coming in and going around, and then warmer water coming out. At every point in the motor, the combination of cool and hot over here is exactly the same as warm and warm here. So all the way around the motor, you get exactly the same cooling. And so you don't end up with hot and cold windings. So nice little way to cool the motor. And with the axial flux machine, you have good access to both sides of the stator to be able to cool the windings nicely. So just going through the parts that are here on the table, this is the resolver. A permanent magnet motor like this, you have to have accurate knowledge of the position of the magnets relative to the stator. And so the resolver does that job. This is a connecting shaft, and that coupler connects the two motors together so that we can give full power from both motors into this gearbox. It's a nice way of being able to stack motors. You can do one or two motors with this setup. This is a carbon brush, and what it does is it helps prevent excessive bearing wear by discharging any static electricity that might be built up. Here we got a spinning plastic rotor that can develop a static charge as it's going and rubbing against the air inside the motor. And that static charge could produce arcing across the bearings and wear the bearings out. And so this dissipates that static charge to prevent bearing wear. So those are the parts. Oh, here we have the electrical connections. It's probably big enough to be a whole inverter, but it's just the three-phase electrical connections from each motor come up here, and you're connected here, and then the three-phase cables for the whole assembly come in here to the inverter. One of Munro Associates' usual comments on this kind of assembly: we're not a big fan of threaded fasteners, except when they are used properly. And there's a lot of threaded fasteners in this assembly. Perhaps not ideal. Maybe we could do some optimizing on this. But for what it is, by the way, it's Powertrains focuses on custom motors for applications like racing or heavy-duty machinery, things that are not 100, 200,000 units. So they're making relatively short run, small samples for different custom industries. This particular one is for motorsports application. So axial flux motors, and how are they different from radial flux electric motors? So this is, when we take this thing apart, all motors have two different parts. The stator, which is stationary. This is one of the two stators in this motor. And then the rotor, which has the magnets, the permanent magnets. These are the permanent magnets. In this case, so the rotor is quite thin. It's a disc. And these magnets would be facing this stator. So this is the part that rotates, and this is the part that stays stationary. There is, in this case, an additional stator underneath this rotor. So it makes a kind of a sandwich. Stator, rotor, and then another stator. And then on the opposite side of this stator would be another one of those housings with the cooling. So it's cooled on both sides. So this two stators are cooled. So that's how this motor is made. The flux path, so the magnets in the middle, the magnetic flux passes axially from the magnets into the stator, and then around the stator, and then back into the next magnet and across over to the stator that's on this side, and then back. So it forms a kind of a loop this way. So the flux that's doing the work is passing axially through the magnets. That's different from a traditional motor where the flux goes radially. This is a Chevy Bolt motor, which happens to be almost exactly the same power and torque and voltage as the axial flux motor here. And so you can see it tends to be a little longer and smaller in diameter. And here the magnets would be in the rotor. I've only taken one lamination of the rotor. The rotor would normally be, long. And then the magnets would be in here, and here the flux from the magnets goes out radially into the stator, and then goes around, and then comes back through the magnets, and then around back to the original magnets, forming a loop like this, and the flux that is producing the torque is moving in the radial direction. So we call this a radial flux motor versus the axial flux motor. The advantage of axial flux motors is that the surface area that you have to transmit the torque with the magnetic field can be larger, so for the same volume. So this surface area is larger for the same volume as the surface area of the inside of this cylinder. So with a larger surface area and about the same magnetic flux, in principle, you should be able to get more torque from an axial flux motor for the same package size. So that's the reason why there's been so much excitement generated about axial flux motors. So what is the trade-off? What is the downside? The problem is that the axial forces from those magnetic material, and there's a real good reason why I don't just pick this up and put it over here, because it takes a crowbar to pull this back off. Very strong magnets don't do something like that, or you pinch yourself pretty badly. So the axial forces have to be reacted by these bearings. And if you don't get the air gap between this side and this side perfectly even, then the axial forces that these bearings have to take up can be quite large. And so there's some issues with bearing wear, bearing design, and and structural strength of the rotor as it's spinning. In this case, by the way, the magnets are retained with this carbon fiber ring. And if they're not retained by the ring, then they will fly apart when it is spinning fast. So as opposed to the radial flux machine, those forces that I was talking about are always contained within the stator. And so the bearings only have to handle the spinning loads, and the axial and radial loads are all balanced. And so it's much easier on the mechanical construction for a radial flux motor. So with different engineering challenges, there's the possibility of getting very high torque and power density from axial flux motors. So that's the potential benefit. It turns out that with all of the real mechanical issues that you have to work with, the actual torque and flux density of this particular machine is about the same as the radial flux motors. And we tend to see that despite some of the claims of some of the companies about spectacular torque and power densities, the actual axial flux motors that are on the market today have comparable, maybe slightly better torque and power density. At this point, from Munro's analysis, the leader in the industry in production motors in torque and power density is the Lucid motor, which is actually a radial flux motor like this. So just for the record, yes, in principle, it's possible theoretically to get very high torque and power densities from this kinds of machine. In practice, it turns out that the highest torque density machine is a radial flux motor made by Lucid. Having said that, there is something about this machine that has me very excited and makes it absolutely perfect for the application that Omni is using it for and their whole business case. And that is how this stator is made. This stator is, usually the stator is one of the most expensive parts to tool up for a motor. This is actually a wound stator, so it's wound like a slinky from a strip of steel. And the strip has these notches cut in it to form the stator slots. So what they've done is to make this, you just run this strip of steel through something called a notching die. And the notching die, a notching machine, is like an industrial sewing machine. It's a relatively inexpensive machine, like $10,000, and the thing operates like a sewing machine, punching little notches into a strip of steel. And then that strip of steel just gets wound up to form this stator. And then in this case, there's 36 slots. So every 36 slots, they just increment the gap between the slots by 1/10 of a millimeter. And when they do that, 36 slots, then 1/10 of a millimeter, 36 more slots, then another 1/10, you end up with, as the diameter grows, all these slots line up perfectly to form straight slots to put the wires in. And now you also have these nice straight slots, and the assembly of the wire, the stator assembly to wind the stator, allows you to just drop these windings directly in to the open slots, versus the kind of stator assembly that's used. This particular one is a bar wound machine, but it's inconvenient to shove these windings down into the slots. In order to do this, you have to break each winding up and then shove them in as hairpins and then weld them on the opposite side, which makes for a more expensive, again, the tooling to make this is significantly more expensive, especially when it comes to that, instead of the notching die that you can use for this one, you tend to use a big stamping die, and you have to stamp out both the stator and the rotor from one big piece of steel. So you have a complex die and a big press, and that stuff costs a lot of money. So the winding process and the stamping die process has large capital cost for this type of motor. And so usually this type of motor you see, you want to tool it up for more than 100,000 units. But again, the business case for Omni Motors is they're making custom motors for each application, for, in this case, a motorsports application. So the customer is only building 10 or 12 vehicles. Well, with a process like this, you can make a custom motor for almost any application with a very competitive cost, because the capital cost is low, even though material cost is about the same. The fact that the capital cost is so low means you can do a custom motor for every application and dial it in directly for whatever your customer needs. So that's the big advantage that we're seeing right now with this Axial Flux motor, especially for applications like motorsports. And sure enough, we're definitely seeing high-end motors going to Axial Flux applications. So that's the thing that as us, real excited here at Munro Associates. Anytime we see great engineering, we love to highlight it, and this is one example. So thanks for joining us here at Munro Live.